Today, we're diving into something we all feel but almost never talk about, the weird, stretchy, totally subjective way we experience time.
I mean, have you really felt it? You know, that feeling where a single second stretches out forever, or maybe a whole hour just evaporates into thin air. It happens to all of us. But what is actually going on inside our heads when time decides to break its own rules?
Okay, check out this absolutely wild example. It's from a police officer's report during a shootout. He said, "In that moment of pure adrenaline, time slowed down so much that the shell casings flying out of the gun next to him looked like beer cans slowly floating through the air." I mean, that's not just a little distortion. That's reality completely warping under pressure.
But it's not always about life or death moments, right? Think about athletes. They call it being in the zone. There's this great story about baseball player Tom Gwynn, who said that when he was locked in, a fastball looked like he was coming in slow motion. So slow, he could actually see the seams on the ball. This tells us that time bending isn't some weird bug in our brain. It can actually be a feature of peak human performance.
And look, you don't have to be in a shootout or a major league game to feel this. We've all been there, staring at the clock, waiting for a class to end or for a pot to boil. It's that feeling where time gets thick, almost syrupy, and just refuses to move. So what's the deal? How can both intense focus and mind-numbing boredom have the exact same effect on time? That's the real question.
Well, to get to the bottom of this, we need a whole new way of thinking about time. A researcher named Susie Vrabel proposes that maybe, just maybe, time isn't the single straight line we always imagine. What if it actually has two dimensions?
Okay, so here's the big idea. You've got length, which is what we usually call time, one event happening after another, tick-tock. But then there's also depth. And depth is all about simultaneity. It's how many different things your brain is juggling and processing at the very same instant. And this is the crucial part. These two dimensions, depth and length, are constantly in a trade-off. When you narrow your focus, really narrow it down to one single thing, like that baseball or the second hand on a clock, the depth of your perception collapses. You're not processing a bunch of things at once anymore. And to make up for that lost depth, your brain basically has to stretch out the length. And that's when time feels like it's grinding to a halt.
So this isn't just some neat psychological trick. It actually has a name, and it comes from physics of all places. It's called fractal time. And what it describes is any process that doesn't have a nice, predictable average timescale. Instead, things happen in these weird, irregular bursts and pauses, kind of like the self-similar patterns you see in a fractal.
Okay, this is where it gets truly wild. Because long before anyone in psychology was thinking about this, physicists were already using the idea of fractal time to explain how charges move through materials like glass or the stuff inside a photocopier. So somehow, the feeling you get waiting for a web page to load is connected to the fundamental physics of solid matter. How cool is that?
And this idea, man, it has a history. It didn't just pop up overnight. The thread actually starts over 300 years ago with a math puzzle from Nicholas Bernoulli. Then, much later, the legendary Benoit Mandelbrot gives the pattern a name, fractal. Then a physicist, Michael Schlesinger, applies it to the physical world. And finally, Susie Vrabel brings it full circle, back to our own consciousness. To see how all these pieces fit, we gotta go back to the start.
So, our story begins with a gambling game from way back in 1713. It's called the St. Petersburg Paradox. On the surface, the game sounds simple enough, but it contains this totally counterintuitive secret about how averages work, or, in this case, don't work.
All right, let's break down the rules. Imagine we're playing. I flip a coin. If it's heads on the first try, you get 1 coin. Game over. But if it's tails, I double the prize, and we flip again. We just keep doing that, doubling the pot every time we get tails until a head finally shows up. So, if you get tails, then heads, you win 2 coins. Tails, tails, heads, 4 coins. Tails, 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 heads, 8 coins. You see how the potential winnings just explode?
So here's the big question that stumped mathematicians for ages. What's the average amount you'd expect to win? Like, what's a fair price to pay to even play this game? Your gut probably tells you it should be some normal, finite number, right? The answer is infinity. Yep. The mathematical average you can expect to win is literally infinite. And that's the paradox. Most of the time you play, you'll win a tiny amount. But that super, super tiny chance of hitting a massive losing streak before you get heads creates a potential payout so huge, it drags the entire average up to infinity. And the physicist Michael Schlesinger put it best. He said that infinity isn't a mistake in the math, it's the signature of a fractal. It means there's no typical scale for the outcome. You can have tiny wins and astronomically huge wins and everything in between. It's just like a fractal, which has detail at every possible zoom level.
Okay, so a 300-year-old gambling game. How in the world does that explain why your kettle seems to take forever to boil when you're staring at it? Well, this is the moment where we connect all the dots. That infinite average from the game, it's not really about money. It's the key feature of any process that runs on fractal time. It means there's no normal amount of time to wait. The event you're waiting for could happen right now, or it could take a shockingly long time. There is no average.
So let's go back to that piece of glass. Imagine its atoms are all jumbled up and stressed. To relax, a little particle has to wander around and find another particle that's stuck. But here's the thing. That little wandering particle moves on fractal time. So just like in our coin game, there is no average time for it to find its target. It's completely random and unpredictable.
And that right there is the final piece of the puzzle. When you stare at a kettle waiting for it to boil, you are collapsing your temporal depth. You're focusing on one single thing. In that moment, your brain becomes the stressed glass, and the water boiling, that's the event you're waiting for. By putting your mind into that state, you are experiencing fractal time. And in fractal time, the average wait is infinite. That's why it feels like it will never, ever happen.
So let's just pull all that together. What have we learned? First, time isn't just one thing. Our perception of it has both depth, how much we're processing at once, and length, the sequence of events. Second, when we narrow our focus, that depth collapses and the length stretches out. And third, this whole experience has a name, fractal time. Unbelievably, it's a real principle that connects our own minds to the physics of glass and even a 300-year-old gambling paradox. It's all connected.
And that leaves us with one last kind of mind-blowing thought to chew on. If our most fundamental experience, time itself, is fractal in nature, what does that say about reality? It suggests that this weird, beautiful repeating pattern isn't just something we see out there in nature, in snowflakes and coastlines. It might be baked into the very structure of our consciousness, the very fabric of how we are.